All right, as we know, we're going to be in class and we won't be rotating. So I decided that it would be better to just continue to review instead of trying to really dive deep into new materials. I hope you got a lot out of the review for water cycle. There are two things going on today. If you were in class, you have 3 sheets of paper that you're going to be working on. For my folks at home, you are just going to be trusted to take these notes in your notebook. Now, some of you might be thinking, hey, sweet, I get to skip doing all this work. If you do that, it's going to catch up with you because some of this stuff that they're writing down are new notes, and you probably don't have them. And they are just putting them on a graphic organizer that I've got to try to figure out a way to get to you. But I don't know how to do that yet, so I'm trying to work on that. Anyway, let's start our review. First and foremost, we have force. We know that a force is a push or a pull. And we see those pushes and pulls around all the time. Today at recess, I saw some people pulling on a jump rope. They're playing tug of war out there, and they were having a good time doing that. I saw some people kicking balls into the air. When I say I saw it, the ball was pulled back down to the ground by gravity. So I saw a lot of pushes and pulls going on. We know that there are pushes and pulls happening around us all the time. Most of you that I saw today were working really, really hard in class, and you were pushing down your pencil, pulling it across the paper as you were working super hard for Miss Klein, taking your notes, and that's fantastic. I'm very proud of those of you that did that. So we had some forces going on there. So forces are a push or a pull. For my people that have the worksheets, you have one that says vocabulary, and it has force, speed, acceleration, velocity, inertia, unbalanced force, balanced force, friction, and work all written down the right-hand side of the piece of paper. All I'm asking you to do is take that piece of paper, and when you see the word force, just flip the piece of paper over. You can kind of see where force would be. Write the definition and give me an example or two. It's not a giant box, so you should be able to fit it. We're going to turn this into a interactive notebook when we get back into class and start working with each other, and I'll figure out what my remote kids are going to do for that. So it's very, very easy. All right, there's force. I would go back and watch this video. It's probably going to help you answer some other questions. But Mr. Bullens, I've already watched it before. Watch it again. This video is one of the best summaries of forces in motion that we have. And it really does give you an insight to the things that you need to know as we move forward. Inertia. We started talking a lot about inertia. And we started talking about that bowling ball that was very, very happy to just sit there in the grass until someone rolled it. And then it was very, very happy to keep on rolling until something like the grass and friction stopped it from rolling. And that's what inertia is. Inertia is the tendency of an object to sit there until a force moves it and to keep moving until a force stops it from moving. And we see those things happening around us all the time. Now, as we started digging into inertia, one thing that we realized, and here's the bowling ball example for you in case you need it, we realized that inertia and Newton's first law, as Nikola so eloquently put it, are exactly the same thing. And they are the same thing. What Newton did was he took inertia and he said, hey, things sit there until something moves it, and they keep moving until something stops it. That's a very simple way of saying that. Let me spice that up with some scientific words, and then honestly start studying it a little bit deeper and figure out what it is. And that's when he came up with an object in motion tends to stay in motion until acted on by a force, and an object at rest tends to stay at rest until acted on by a force. And that's where we get Newton's first law, or as it's called, the law of inertia. For those of us working in class, you actually have a square piece of paper that has a square in the middle of it, and it says Newton's first law at the top. And it has friction, which we just went over. Well, I think we're going to go over in a minute. It has inertia, which we're most definitely going over now. And then it says list some examples of Newton's first law. Well, I mean, if I were you, I think an easy example is to kind of come back maybe a slide or two and talk about this, how a bowling ball would still sit there. And get into that a little bit. And you can use any example that you want to. That's fine, as long as you're talking about Newton's first law. That'll get that one done for you. And then you have the word inertia on your vocabulary with all the vocabulary on the right-hand side. You can just jot it down there. And those of us at home are just jotting these things in our notebook for right now. All right, let's see what's next. Here's a fun cartoon. There's this really annoying little boy that I hope Newton catches one day and gets rid of. And he's always pestering Newton. But this cartoon tells you all about Newton's first law. And maybe you want to use some examples out of it to help you take some notes or to write things on those pieces of paper that we have in class today. This is that Wonderopolis about inertia that I shared, and I don't think a lot of people really went through this at all. I'm going to say go ahead and go through this because on the next upcoming test, you never know, there could be possibly maybe some extra credit questions on there that come straight from this. Don't know if that would happen or not. I make the test, so we'll have to wait and see if that's what happens. Here's a fun video for you to watch to help you out a little bit with inertia. Then we come to Newton's second law. And when I got to Newton's second law, people were like, oh man, this is going to be hard. And then when I told you what it was, you were like, Mr. Bullens, we kind of already knew that. And I was like, yeah, but now you know the fancy technical terms for it. Again, we gave that example. I think it was Ray. It was in class. And I was like, if I asked Ray, hey, Ray, take these, 5 books down to the library that were in that milk carton, he would say, sure thing, Mr. Bullens, no problem. He would pick up the 5 books and he would go down the hall and it wouldn't be a big deal. However, if there was 1,000 books, he would look at me like I'm crazy and he'd be like, Mr. Bullens, I can't move that. It's too heavy. That's exactly what Newton's second law is. The more mass you have, the more force you need to get it moving. Remember those 3 dudes? I keep wanting to say 2. Remember those 3 guys up in the woods trying to move that giant boulder? I mean, we watched like a 4-minute video of them and they hardly budged that boulder at all. And you're looking at me like, Mr. Bullens, why are you wasting 4 minutes of my life to show you that the greater the mass of an object, the more force you need to move it? Because in the very next slide, we watched this old guy hurling these rocks across this lake, and they were skipping like 75 times. Yeah, he's a world champion, like rock skipper. I can't believe that that's a thing, but he is. But the reason why he was able to move those little stones and those guys could not move that big rock all boils down to Newton's second law. The more mass you have, the more force you need to move it. Those little rocks don't have a lot of mass. They don't take a lot of force to skip them across the top of that lake. That big boulder has a ton of mass, and obviously it takes more than 3 guys to move it. Newton's second law. Here's the annoying little kid in Newton again. You can kind of get a little bit more of a detailed insight of that. Newton's third law. This is the one that we haven't dug into very much in class. And I know that there is a sheet that says Newton's third law, and it says to explain how a rocket is able to lift off, explain what would happen if you stand on a skateboard and then push a wall, like if you're standing on a skateboard facing the wall and you pushed, and explain what would happen in your own words if you were to let an untied balloon go, and then you have to tell me why. And it all boils down to Newton's third law, which says for every action, there's an equal and opposite reaction. On top of the school somewhere is a really cool bouncy ball. It's like this super high bouncy ball. And we took it outside and I held the ball at about like maybe chest high. And I said, all right, class, I'm just going to let this ball go. Who thinks it's going to bounce over the school? And everyone said, no, Mr. Bullens, that's not going to bounce very high if you just let it go. I was like, well, how do you know that? They're like, because you're not using a lot of force. I'm like, oh, wow, my lessons are starting to make sense to you. I was like, what if I slam it as hard as I can? And they're like, maybe. Well, we got out into the bus parking lot and tried it, and, well, I didn't use enough force, so now it's on top of the school. So that's something that you can look at. But again, that's every action has an equal and opposite reaction. When I barely let the ball go, it barely bounces. When I slam the ball down on the concrete as hard as I can, it gets a lot more of a reaction. You expect it to bounce very high. We just did not put enough force in it to bounce it over the school. And that's okay, not a problem. We'll get another one of these days. But that's essentially what Newton's third law is. So when you think about it, are you really shocked that a rocket, when it starts pushing against the earth with all of that force, that it's able to lift itself up off of the earth and into the atmosphere? No, because it's using an immense amount of force. Okay, you're not going to expect like the little elf on the shelf to come out from like under the thing and go and it launch, because that's not enough force to move anything. Like, we're not shocked by that. We're not shocked by the fact that a giant rocket with all of that force pushing behind it moves it. Okay, if we are standing face to face with each other and we're standing in roller skates and we barely push each other, we're barely going to go backwards. If we shove as hard as we can, well, we're going to move even further backwards than we're normally used to because we used a lot of force. Here's the annoying little kid in Newton again for Newton's third law. Here's another video that's going to help you out with Newton's third law. Balanced and unbalanced forces takes me back to the front of my vocabulary sheet, and these are two different forces, so you know that these are pushes and pulls. And I think we even talked about it. Something like an earlier definition said like force is a push or a pull that causes movement, and I said I don't like that definition because sometimes there are forces that don't cause movement, and that's where we get to balanced and unbalanced forces. If we had a seesaw and we were able to actually get on the seesaw, and we had two people on one side and they were the same size, and two people on the other side and they were the exact same size as the other two people, we wouldn't expect the seesaw to move because the seesaw would be balanced. The forces pushing down on both sides are equal, so the seesaw wouldn't move. Another example is tug of war. If there's two people on one side and two people on the other side and they're pulling at the exact same amount of strength, the rope doesn't really move. However, in an unbalanced force situation, you have movement. If we took 6 people and put them on one side of the seesaw and one tiny person and put them on the other, we would all expect the 6 people to go down and the little person to go up because the forces are unbalanced, and you actually have movement with unbalanced forces. Balanced forces, no movement. Unbalanced forces, you do have movement. Same thing with the tug of war. If you have 2 people on one side and 2 on the other, but one side is pulling harder than the other side moves towards the side that's pulling harder. We've all seen that in our tug of war. Sorry, things kind of got glitchy there. When we have one side of tug of war pulling harder than the other side, we have movement because that is unbalanced forces. Balanced forces and unbalanced forces. Here's a good example, and again, you'll notice that tug of war comes up a lot when we're doing these because it is really an easy way to understand it. This side is pulling with 400 newtons. Remember, that's force. This side is pulling with 400 newtons. They are equal, so there is no movement. This is balanced. This side is pulling with 500 newtons, while this side is pulling with 300 newtons. Now we know they're pulling harder, so that's going to go this way because we have unbalanced forces. Here's a very short video, and what a shock. They're doing tug of war to show balanced and unbalanced forces. Trust me, that comes up a lot. That's even in the questions about that. So be ready to see that. That shows up very, very often. Here's a question you have to answer. Are the forces balanced or unbalanced? And yes, I am trying to trick you because sometimes you're not pulling away from each other. You're pushing towards each other. But it's the exact same thing. If you're pushing with the same amount of force, it's balanced. If you're pushing with different amounts of force, it's unbalanced. Friction. We've talked about this. When two objects collide against each other, friction makes them stick together. Depending on the two objects, they either don't stick together well or they do stick together very well. Basically, what we know is friction slows things down and stops them. If we roll a ball outside in the grass, we don't expect it to roll forever because we know that friction slows things down. A new definition, well, I mean, it's not new, we've had it already, but speed. Speed equals distance divided by time. Again, we know speed is how fast an object is moving in a given time. What does that mean? If Mrs. Mills drove 120 miles in 2 hours, so you have distance and time, distance divided by time is speed, 120 divided by 2 is 60, she's going 60 miles an hour. Now, you don't have to memorize all this now, you will, it's coming. But we're going to get to that soon. But how fast an object moves. Acceleration. I know it's a change in velocity with respect to time, but let's make it easier. Acceleration is when things speed up. When your parents are driving down the road, they get on the highway, they get on an acceleration ramp. It's time for them to go faster as they get on the highway. Acceleration. The opposite of acceleration is deceleration. When you decelerate, you slow down. So let's make those two definitions a little bit easier for us. Accelerate, speed up. Decelerate, slow down. Velocity, just know the speed and direction of a moving object for now. We probably won't even have time to dig deep into velocity, honestly and truthfully. Just get that definition down for now and you will be fine. I hope you enjoyed this brief review of forces in motion. Don't forget to smash the like button and subscribe, and good luck on the benchmarks.